Spiraling in frozen fractals all around, and one thought crystallizes like... Oh, I didn't see you there. One of my favorite things on this planet is the movie Frozen. But what tops that is fractional dimension, and that's what I'm going to be talking about today.
Fractional dimension. So if you look at Elsa's hand, you see the snowflake right above there, and that's a perfect example of what we'll be talking about today. So what is it? Well, let's start with dimension. Dimension is dependent on the planes of an object, and it's related to the length, the width, and the height. And to make copies of something, the dimension would have to be to the exponent or to the power of a scale. With fractals, there's no whole number dimension. So what is fractional dimension? Well, it's this complex, never-ending pattern that's created by these repeated mathematical equations. And it's really cool because it's something that can be found in technology and in nature. It's characterized by having an infinite perimeter with a finite area. Now, what's its origin? Well, Mandelbrot worked with fractals dating all the way back to 1975, and they were explained as geometric shapes that, when divided into parts, would become a smaller replica of the whole shape. Now, research with the investigation of nature allowed further theorems to develop regarding fractional dimension, which is part of the reason the generalized Fatto-Julia theorem came into existence. So, what are some examples? Well, there's the classic examples of the 3D coach snowflakes, or Pascal's triangle, where the number pyramid has every number as the sum of the two numbers before. Confusing, I know. The Sierpinski gasket, on the other hand, to the left is an equilateral triangle with the center of each segment cut out. So, what about in nature? Those are the most fascinating examples to look at. We see fractional dimension in river systems, lightning bolts, galaxies, biology with chromatin found in DNA, ferns and cauliflower, and even our blood vessels. So, what's the big idea? It all surrounds this concept of a simple equation to produce these images of beauty. C equals S to the D. Now, the C represents the copies, the S represents the scale, and it's to the power of the dimension. So with the reverse, you can also find the dimension of a given shape using logs and find the copies using exponents. But to sum it all up, fractional dimension is a ratio, and it's a fundamental concept in mathematics that deals with how complicated a self-similar structure is. And it is truly fascinating.
You know what? If there's one thing that you take away from this presentation, I want you to remember how amazing fractional dimension is. But in the words of Queen Elsa herself, let it go, I'm one with the wind and sky. Here I stand in the light of day. Let the storm rage on, the cold never bothered me anyway.